All right, so before the break, we looked at what a logarithm is, and we saw that the logarithm is the inverse of an exponential function. We saw that we can convert between the two forms by starting with the base and cycling through, because the base in either form is the same. A logarithm has a base. An exponential function has a base. And when you convert from one to the other, the bases stay the same. And then to get the order that the other pieces are written in, we start with the base and cycle through. If no base is indicated for a log, that means it's a common log, base 10. And you can use the log button on your calculator in order to evaluate that. We saw that if the base is something other than 10, as of right now, what we need to do normally was convert from logarithmic to exponential and then work from it from there. We will learn how you can deal with logs with other bases very soon, but for now, we're just evaluating logs with base 10 using the log key. If the base is something different, we convert it from logarithmic to exponential, and again, work with it that way. So, question A says, state the inverse of f at x equals 3 to the power x. So, remember that instead of f at x, we can write it as y equals 3 to the x. And remember, to get the inverse, your first step is to interchange x and y. So x will equal 3 to the power y. That is one form of the equation of the inverse. You also should remember that when you want to write an equation of the inverse, we always put it in the form y equals. So you have to get y by itself here. And there's no mathematical step that you can do to get y by itself, meaning you can't take the y root of both sides. That's not going to help you. All right? So what we would do is we would convert from exponential form to logarithmic form. So remember that in either form, the base is the same. Because the exponential form has a base of 3, the log will have a base of 3. And to get the order the other pieces are written in, we start with the base and we cycle through. After the base 3 comes the x, and after the x comes the y. There's the equation of the inverse. The equation of the inverse would be y equals log base 3 of x. Right? Then it asks us to sketch the graph of this inverse. Sketch the graph of y equals log base 3 of x. Well, as of right now, we cannot use that equation to sketch the graph because we have no way to evaluate logs with a base of 3. Right? But what we can do is we can use the equation that we wrote above here, x equals 3 to the power y. So we're going to use that equation, x equals 3 to the power y. That is the inverse of the original expression. Now, normally when we do a table of values, we start with our x values and find out what y equals. In this case, we'll have to do the opposite. We'll have to start with y values and then get the x value. Because the way it's written, y is the independent variable. X would be the dependent variable. The answer you get for x depends on what you put in for y. So I can use different values for y. And then find out what x equals. For example, when y is negative 2, 3 to the negative 2 will be 1 over 3 squared, or 1 over 9. When y is negative 1, 3 to the negative 1 will be 1 over 3 to the positive 1. When y is 0, anything to the power 0 is 1. When y is 1, 3 to the 1 is 3, 3 squared is 9, 3 cubed is 27. So this gives us some points that we can put on our graph for the inverse of y equals 3 to the x. I've got the point 1/9, comma, negative 2. I've got the point 1/3, comma, negative 1. I've got the point 1, comma, 0, 3, comma, 1, 9, comma, 2, which I'll have to kind of estimate where that is, and I don't really have room to put the other point on there, the point 3, comma, 27, but that's okay. We've got enough points to sketch this graph, right? So We sketched, or we got our table of values by using x equals 3 to the y. That is the same as y equals log base 3 of x. And we did see what the graph of a logarithmic function looks like before the break. The logarithmic function, unless it's been shifted left or right, will have a vertical asymptote on the y-axis, which is the reason why that you cannot take the log of 0 or the log of a negative number, because this graph will be always on the right side of the y-axis. The y-axis acts as an asymptote. The line x equals 0 because x cannot equal 0. And that's our graph. So not only can we say that's the graph of the inverse, x equals 3 to the y, we can also say it's the graph of the logarithmic function y equals log base 3 of x. They are the same equation. They're just written in different forms. So now that we have the graph, we can fill in those characteristics, right? The domain of this will be from 0 to positive infinity, neither included, which is why we use those rounded brackets. The range will be from negative infinity to positive infinity. Goes up and down forever. The x-intercept is at the point 1, 0. The y-intercept does not exist. The y-axis is an asymptote. And so the equation of the asymptote, remember an equation must have a variable and an equal sign. That is the line x equals 0. Okay. So we can do the same thing for this one. We're asked to write the inverse of f at x equals 1/2 to the power x. So again, if instead of f at x equals, we're going to write y equals 1/2 to the power x. And then the first step for the inverse is interchanging x and y. But most equations are in the form y equals. So we can write this in the form y equals by changing its form from exponential to logarithmic. Remember, the bases are the same in either form. The exponential function has a base of 1/2, so the log will have a base of 1/2. And to get the order the other pieces are written in, we start with the base and cycle through. So it'll be log base 1/2 of x equals y. So there's the equation of the inverse. These are both equations of the inverse. They're just in different forms. The first form is exponential. The second form is logarithmic. And the reason we do that is because usually we have our equations written in the form y equals. To sketch this, again, we will use a table of values. And because we don't know how to evaluate logs with bases other than 10, except changing each one from logarithmic to exponential and trying that. So instead of doing it that way, we will do it by using the exponential form. X equals 1/2 to the power y, where y is the independent variable. So again, we'll start with values for y. -3, -2, -1, 0, 1, and 2. And you can use any values you want for y. These are just the values that I chose. When y is -3, 1/2 to the -3 will be 2 over 1 to the positive 3, which is 8. When y is -2, 1/2 to the -2 will be 2 over 1 to the positive 2, which is 4. 1/2 to the -1 will be 2 over 1 to the positive 1, that'll be 2. When y is 0, it doesn't matter what the base is, anything to the power 0 is 1. 1/2 to the power 1 is 1/2. 1/2 squared is 1/4. So because the base is between 0 and 1, we saw before the break, that'll give us a decreasing function. I got the point -3, 8, which is up here somewhere. I've got the point, I'm sorry, I did that backwards. It should be 8, -3. So I will fix that. 8, -3 will be down here somewhere. The next point is 4, -2, 2, -1, 1, 0, 1/2, 1, and 1/4, 2. Again, the x-axis is our, the y-axis is our asymptote. So there's the graph of that logarithmic function. It is a decreasing function because the base is between 0 and 1. But it doesn't change our domain and range. The domain is the same as the previous one. It goes from 0 to infinity, neither is included. Our range goes from negative to positive infinity. The x-intercept hasn't changed. It's the point 1, 0. There is no y-intercept. Graph doesn't cross the y-axis. The y-axis is our asymptote. And our asymptote, the equation of, remember, has to have a variable, has to have an equal sign. The y-axis is the line x equals 0. Okay? On the next page, without using technology, estimate the value of y of log base 2 of 14. So if we want to estimate its value, let's let it equal y. And the reason we have to estimate, because as of right now, we don't have any way to evaluate logs with other bases besides base 10. So what I would do here is I would again convert from logarithmic to exponential. I'd start with the base and cycle through. Remember, the base in either form is the same. The log has a base of 2, so the exponential form will have a base of 2 as well. And so that'll be 2 to the power y equals 14. So we want to know 2 to what power will equal 14. Well, we know that 2 cubed is 8, and we know that 2 to the 4th is 16. Our number of 14 is between 8 and 16. So our answer has to be between 3 and 4. Because our number 14 is closer to 16 than it is to 8, our answer will have to be closer to 4 than it is to 3. So we might approximate y approximately equal to maybe 3.8. Approximately. We can find out how close we are by using a graphing calculator. My first equation will be 2 to the power x. My second equation will be y equals 14. And I can find out the point of intersection between these two. If I go zoom 0 for zoom fit, and it graphed y equals 14 really, really low here. And unless you were watching carefully, you wouldn't have seen it. And we can't really see that line, so that just means we need to change our windows. I will change my y minimum, let's say, to -2, and my y max to +16 instead of 1024 is what they had. I'll change my y scale to 2. Now when I graph it, I can see that line y equals 14. I can find my point of intersection. Second function trace. Number 5 for intersect. Enter, enter, enter. Try that again. Second trace. Number 5 for intersect. enter, enter, enter. There we go. And my estimate was fairly close. Calculator says it's 3.807, and there's more decimals. We guesstimated it to be 3.8, which is very close. So we guesstimated, we estimated without using technology, and then we used technology to see that our estimate was fairly close. Okay. And then we can do the same thing for estimating the value of log base 3 of 50. So again, if we say y equals log base 3 of 50, we can convert from logarithmic to exponential by starting with the base and cycling through. The exponential form will be 3 to the power y equals 50. So we know that 3 cubed is 27. We know that 3 to the fourth is 81. Our number 50 is between 27 and 81. Okay. It is closer, a little bit closer to 81 than it is to, well, that's not true. It's not really closer to 81 than it is to 27, because if we take the difference between 50 and 27, that's a difference of 23. Between 81 and 50, so it is closer to 27 than it is to 81. However, we're going to see that our answer is actually closer to 4 than it is to 3 because of what an exponential function does, right? So, I mean, you could definitely use your calculator to help you narrow down your search. For example, if we went 3 to the power 3.5, so we need to get an answer of 50. So we're close, but it's going to have to be a little bit greater than that. So if we went 3 to the power 3.5, I don't know, 5, let's say, now we're pretty close to 50. So that would be our guess. Y would be approximately 3.55. And we saw before that we could use our calculator to graph these two functions to find out a more accurate answer. Now, because my second equation is y equals 50, my y max must be at least 50. Bless you. So if we change it to, let's say, 52, and maybe use a scale of 4 now on the y-axis. Second function trace, number 5 for intersect, enter, enter, enter. So a more accurate answer would be 3.56, which is pretty close to what we guesstimated it at. But as of right now, we have no way to algebraically determine what log base 3 of 50 is. So we're going to get to that. How you deal with logs with bases other than 10. But before we do, let's look at a couple applications of logarithmic equations. In 1935, the American seismologist Charles Richter, so now you know where the name the Richter scale came from, he developed a scale formula for measuring the magnitude of earthquakes. The Richter magnitude m of an earthquake can be defined as m equals log of a over a sub 0, where a is the amplitude of the ground motion, usually measured in microns, measured by a sensitive seismometer, and a sub 0 is the amplitude corrected for the distance to the actual earthquake that would be expected for a standard earthquake. Now, you're never going to be asked to figure out what a is or a sub 0 based on what the description is. For example, you won't be asked to find or be able to figure out what the motion in microns of the ground shake or the amplitude corrected for distance to the actual earthquake that would be expected for a standard one. You're not going to have to figure out what those are based on those descriptions. So we'll see how this equation is going to be used. So in 1946, an earthquake struck Vancouver Island off the coast of BC. It had an amplitude that was 10 to the power of 7.3 times a sub-zero. What was the Earth's magnitude on the Richter scale? The earthquake's magnitude on the Richter scale. So we want to know what m is. And if we use that formula, that m, the magnitude, is the log of a over a sub-zero. For part A, we are told that the amplitude, which is what A is, was 10 to the power 7.3 times a sub-zero. So A is 10 to the power 7.3 times a sub-zero over a sub-zero. So I'm just using the formula that we were given, and we are told that A, the value of A is 10 to the point 7.3 times a sub-zero. That's what it tells us right there. And so the a sub-zeros will cancel, and you will have log of 10 to the power 7.3. Now, there is no base indicated for this equation, which means it's base 10, which means you can evaluate this using the calculator and the log button. We can go log of 10 to the power 7.3, which is 7.3. And it's not a coincidence that the answer is the exponent. And we're going to learn why that is true as we start looking more at logs and the laws of logarithms. Okay? We will see why that is true. But that was the magnitude of that earthquake. That was the number, the reading off the Richter scale. The magnitude is 7.3. Part B says the strongest recorded earthquake in Canada struck off Haida Gwaii, which used to be the Queen Charlotte Islands. It's west of Prince Rupert. In 1949, it had a Richter reading of 8.1. How many times as great as a sub-zero was its amplitude? So in this case here, we're given the magnitude. It's 8.1. We are told that the magnitude is 8.1. We want to know how many times as great as a sub-zero was its amplitude. So in this case, we need to get A by itself, and it'll be a function of a sub-zero. So we need to get A by itself. Now again, this is a common log, no base indicated, which means it is base 10. If we convert from logarithmic form to exponential form, it'll be 10 to the power 8.1 equals A over a sub-zero. If you start with the base and cycle through, that's what you get. And remember, we want to know what A is in terms of a sub-zero. So if you take this expression that we have and you multiply both sides by a sub-zero, you'll have A by itself. A will be 10 to the power 8.1 times a sub-zero. And we can put an actual number on that by going 10 to the power 8.1. And this will be how many times as intense A is compared to a sub-zero. So that's 892,541.2 times. 125,892,541 times a sub-zero. So there's our answer to part B. Part C asks us to compare the seismic shake of the 1949 Haida Gwaii quake with that of the earthquake that struck off Vancouver Island in 1946. So we want to compare them. We want to know how many times more intense one is compared to the other. Now, the Haida Gwaii quake was the one that was more intense. So what we will do to compare these, we will take the amplitude of the Haida Gwaii quake, and we will divide that by the amplitude of the Vancouver Island quake. The amplitude of the Haida Gwaii quake is 10 to the power 8.1 times a sub 0, whereas the amplitude of the Vancouver Island quake is 10 to the power 7.3 times a sub 0. And I'm just using the relationships that we developed above. So the a sub zeros will cancel, and your answer will be the answer you get when you divide 10 to the power 8.1 by 10 to the power 7.3. So you're dividing powers with the same base. Remember, the laws of exponents say that you subtract the exponents and keep the base the same. So it'll be 10 to the power 8.1 minus 7.3, which will be 10 to the power 0.8, and 10 to the power 0.8 is approximately 6.3 times as intense. Okay. The largest measured earthquake struck Chile in 1960. It measured 9.5 on the Richter scale. How many times as great was the seismic shaking of the Chilean earthquake than the Haida Gwaii earthquake, which measured 8.1 on the Richter scale? So again, as we saw in the previous question, we can compare them by dividing the amplitudes. The amplitude of the Chile earthquake divided by the amplitude of the Haida Gwaii quake. And again, we developed this relationship that the amplitude is a factor of a sub 0. The Chilean quake, which measured 10 or 9.5, we also saw that the amplitude in terms of a sub 0 was 10 to the power of the Richter scale number. So for the Chilean quake, it'll be 10 to the power 9.5, because that is the measure on the Richter scale, times a sub 0. And the Haida Gwaii quake had a Richter measure of 8.1. So its amplitude is 10 to the power 8.1 times a sub 0. Again, the a sub zeros cancel, and your answer will be what you get when you divide 10 to the power 9.5 by 10 to the power 8.1. Again, when you're dividing powers with the same base, you subtract the exponents and keep the base the same. So that'll be 10 to the power 1.4. Which is approximately 25.12 times as intense. Now, on a diploma exam, you will not be expected to come up with these relationships on your own like we did. I showed you where they came from, but you wouldn't be expected to come up with those relationships. If you had a question like this, they would give you the equation that you need to use. And chances are you'd have to convert from logarithmic to exponential to help you solve it. Start with the base and cycle through. But you wouldn't be expected to come up with these relationships on your own. Okay? So, for practice, you should work on these questions. I will post the solutions on Google Classroom so you can check your answers. I would encourage you to do those to get that practice in, working with the exponential and logarithmic equations. Okay?